Hello, future engineers. This is 2D frames, part 2. So I'll discuss levels 6 to 10 in this video. For the frame shown, determine the magnitude of the pin reaction at B. Neglect the weight of the frame. So here is the given figure. So first, let's draw the free body diagram of portion BC because we can analyze the component reaction at B. So this is the free body diagram. Call that BH, CH, vertical reaction at B, and vertical reaction at C. So we set moment at C0 to solve for BH. F1 is the area of this loading triangle, and this distance is 1/3 of 1.8, so that's 0.6 meter. So therefore, moment at C equals 0, and it is equal to BH times clockwise positive BH times 1.8, then minus F1, which is area 1/2 or 0.5 of 1.8 times 15 times 0.6. From there, we can solve BH, which is equal to 4.5 kilonewtons rightward. We then transmit BH to the other left portion of the frame, and vis-a-vis is now downward. Then we set moment at A0. So we don't need to put the component reactions at A because they are not involved in the moment summations at A. Or you may put, but it's useless because we only need vis-a-vis to solve for reaction, pin reaction at B. So clockwise positive again. So it is equal to vis-a-vis times 2. Then F2 is also clockwise. So plus area of this triangular loading, 1/2 or 0.5 of 3 times 12, then moment arm 1. Then minus 4.5 times 3. So from here, we can solve vis-a-vis. Vis-a-vis is equal to negative 2.25 kilonewtons. Finally, we can now compute the pin reaction at B, square root of 4.5 square plus 2.25 square. The sign does not matter because we are just required to compute the magnitude of the pin reaction at B. So the pin reaction at B, RB, is equal to 5.031 kilonewtons. Next, the bars AB and AC are joined by a pin at A and a horizontal cable. The vertical cable carrying the 200 kilogram mass is attached to the pin at A. Determine the tension in the horizontal cable and neglect the weight of the bars. So here is the given figure. So we'll call the reaction at C R sub C because it is just a roller vertical. At B, because there are no inclined loading, so it's vertical reaction and horizontal reaction. The horizontal reaction is 0, obviously. Then for the distance, this is 5 cosine of 30 degrees because this is also 30. And it is equal to 4.330. Use your calculator there. Then tangent of 30 degrees is this opposite divided by 5. Therefore, this is 5 tangent 30 degrees. While this distance is 3 meters sine of 30, so that's 1.5 meters for the moment arm tension later. Then as I said, this is tangent 30 is distance AB over 5. So this is 5 tangent 30 in decimal 2.887. Because this is 60 degrees, this is also 60 degrees, 90 degrees there. So this is 2.887 cosine of 60. 2.887 cosine 60 is 1.4435 meters. So let's need R sub C considering the whole system by setting moment B 0. So counterclockwise positive. So we have R sub C times quantity 1.4435 plus 4.330. Then minus 200 times 9.81 times 1.4435 to convert it to newtons. So R sub C can now be computed. It is equal to 490.54 newtons. Supposedly, we're going to isolate the free body diagram of this member. So we have tension here. And since we plan to sum up moments about A or moment A0, although there are pin reactions at A, then all forces acting at A will not be involved in the moment equation. So it's useless. Just imagine that this is isolated and we take moment A0. So these are the only forces involved, tension and R sub C. So considering clockwise positive, so we have tension times 1.5, then minus R sub C, which is 490.54 times 4.330. So from there, we can solve for the tension, and it is equal to 1,416 newtons. For what value m of the clockwise couple will the horizontal component AX of the pin reaction at A be 0? If a couple of that same magnitude m were applied in a counterclockwise direction, what would be the value of AX? So here is the given figure. Let's just assume AX is in that direction, and if we isolate member AB, because the loading is 150 at the center, definitely the vertical reaction at A will be half of 150, so it is 75. Then at B, it's not important because we're just computing for that moment M, so we'll consider the entire system. Again, this 75 here is half of 150 if you isolate AB and you analyze member AB, but obviously it is 75 half of 150. So there's no need to prolong lengthen the solution because it's simple as that. The explanation is simple. Then the component reactions at C, you just put it there. This horizontal distance is 4 cosine 60, so 2 feet, then plus 3, so this distance is 5 feet. Then the vertical distance is 4 sine of 60 degrees. 4 sine 60 degrees is 2 square root of 3 feet. So let's just first assume that AX is not 0 because we are required to solve for AX in the second part. So moment summation at C0, counterclockwise positive. So we have AX times 2 square root of 3 plus 150 times 5. Then minus 75 times 3 plus 5 is 8. Then plus the couple or moment, which is, sorry, minus, because this is counterclockwise, minus m. So take note that in the first part, AX is 0, so this term is 0. Then m is equal to 150 times 5 minus 75 times 8. So the magnitude of moment is 150 pound-foot, and it is correct, it is clockwise. In the second part, we are asked to compute, to determine AX if moment of magnitude 150 is now acting counterclockwise. So it's now counterclockwise, remember. But we will not draw another figure. Just imagine that this is counterclockwise. So we use the same equation, except that this m here becomes positive m because it is now counterclockwise. Same sense as the moment of 150 as well as AX. So we just copy everything except that this minus m becomes plus m, and m is 150. So AX times 2 square root of 3 plus 150 times 5, then minus 75 times 8, then plus 150. Then this time AX is unknown. Then AX is 75 times 8 minus 150 minus 150 times 5 divided by quantity 2 square root of 3. So AX is negative 86.6 pounds. So that means AX is rightward. AX is 86.6 pounds rightward. But the question is just the value of AX. So the value of AX is 86.6 pounds for that case. Determine the magnitude of the pin reaction at A and the magnitude and direction of the force reaction at the rulers. The pulleys at C and D are small. So here is the given figure. So by principle in the preceding part on how to put the FBD for this cable system. So we have to apply that this tension is 60 times 9.81. Anyway, the pulleys are very small, so meaning to say it still acts at the pin or not at all, but this distance is the radius of the pulleys will be negligible. So 60 times 9.81, downward also is 60 times 9.81. Here it's 60 times 9.81. Then the angles, the horizontal reaction at A, assume rightward. Then the vertical upward, just as an assumption. Then the reaction at F, let's just assume that it is upward. Then this angle is arctan of 0.5 over 0.4. That's 51.34 degrees in your calculator. This angle, the measure of this angle is arctan of 0.5 over 4.4 times 3, 1.2. Arctan of 0.5 over 1.2. That's 22.62 degrees. So first, to solve for a vertical moment F0, clockwise positive, so equals AV times 0.8. This tension has two components, horizontal, which passes through F, so no moment, and the vertical, which is 60 times 9.1 sine of 51.34, and it is clockwise, so times 0.4, plus 60 times 9.81 sine of 51.34 times 0.4, then plus 60 times 9.81 times 0.4, then minus the vertical component of this tension because the horizontal passes through F also. So minus 60 times 9.81 sine of 22.62, moment arm is 0.4. So we can solve AV, use your calculator there. AV is equal to negative 410.92 newtons. So meaning to say I wrongly assigned the direction, so it's downward. So it's good that we sometimes experience a situation where the direction is wrong, so that you know how to correct it. But there's no need to correct because we are just asked to compute for the magnitude and the pin reaction at A. Then after AV, we set moment A0 to solve for RF. So this time counterclockwise positive, so RF times 0.8, then plus the vertical component of this tension, plus 60 times 9.81 sine of 51.34 times moment arm 0.4, then plus the vertical component of this tension, 60 times 9.81 sine of 22.62 times 1.2 moment arm, then minus 60 times 9.81 times 1.2 also. So only RF is unknown here. Solving for RF is positive, so therefore it's upward, and that's the direction of RF and the magnitude. Finally, for AH, we set R horizontal 0, horizontal component of reaction 0, considering this free body diagram. So it is equal to AH, then minus the horizontal component of this tension, which is 60 times 9.81 cosine of 51.34 degrees, and minus the horizontal component of this tension, 60 times 9.81 cosine of 22.62. Solving for AH is 911.02 newtons. Finally, the pin reaction at A is square root of AH 911.02 square plus AV, which is 410.92 square. So RA is equal to 999.4 newtons. Determine the horizontal and vertical components at C, which member ABC exerts on member CEF. So this is the frame given. First, let's have the reactions at F, vertical only because this is a rocker. And at A, horizontal, which is obviously 0 because there are no inclined loads. And the vertical is a V, let's say downward. So first, set moment F0 considering the entire system. So we have AV, counterclockwise positive, times 1.8. Then minus 1,500 times 0.9 plus 0.3 radius, so 1.2. So AV is correct downward. It is equal to 1,000 newtons downward. So if AV is downward 1,000 plus another downward 1,500, so meaning to say RF by summation force vertical equals 2,500. So I just put it 2,500 upward to shorten the solution. Anyway, I mentioned it 1,000 downward plus 1,500, so that's 2,500 upward. Then we draw the FBD of BAD. So this would be the, by principle, remember that if we have tension here, then we put the tensions at the center of the pulley and we remove the pulley. So this is the FBD. We need to solve for vis-a-vis by, this is 0.9 because B is the center of this member. E is also the center of this member. So that's 1.2, 1.2. That's why it's the center. So therefore, this 1.8 is also divided by 2. So that's why this is 0.9 and this is also 0.9. BE is 0.9, then ET is also 0.9 as given in the figure. So moment at E0, counterclockwise positive. So vis-a-vis times 0.9 minus 1,500 times 0.9. So that means the vis-a-vis is downward and it is 1,500. Then if vis-a-vis is 1,500 plus 1,500, so that's 3,000. Therefore, vis-a-vis is 3,000, 1,500 plus 1,500, and it is upward. So I do not show it anymore also because I already mentioned it to shorten the solution. Then we draw the free body diagram of CEF. So in this CEF here, we can solve, so EV, which is upward, is now applied here by action-reaction principle, 3,000 downward. EH, which is rightward here, should now be leftward here. And this 2,500 RF remains 2,500 upward because it is an external reaction. Remember the principle. Then at E, because there is tension here of 1,500, so that's why we have 1,500 there. Remember the principle, which we solved in part 1. And this distance is 0.3 because the radius of the pulley is 0.3. So 1.2, 1.2. Let's solve for C sub V first. Although we can solve CH first if you want to, but just C sub V by setting R vertical 0 in this free body diagram. This is the free body diagram also of this part of the frame. So BH leftward here, so it's rightward. BV downward, so it's upward here. CH rightward, so leftward here, and C sub V upward, downward here. And these external reactions remain unchanged, 0, then downward AV 1000. But we need only CH and CV. Actually, we can answer it from here. So RV vertical in this free body diagram, so 2000 equals 2,500 minus 3,000 plus C sub V. So C sub V is 500 newtons, and it is upward here. So in the question is determine the horizontal and vertical components at C which member ABC. This member ABC exerts on member CEF. So we base our final answer on this free body diagram. Because C sub V is 500 newtons and it is downward here, so our final answer, C sub V is 500 newtons and it is downward. Unless otherwise it is negative, so it is upward supposedly. Then CH, we set moment E0. clockwise positive, so equals CH times 1.2 plus 1,500 times 0.3. So that means CH is equal to negative 375 newtons. Because CH is negative 375 and in this member ABC here it is leftward. So the correct direction of CH as it acts on member ABC is rightward. So the answer is CH is 375 newtons rightward. So that's it for this part.